Okay, I want to talk about white semimetals. I don't remember even the title of my talk. We had no time to look into the program. Anyway, so good. So why do I like topology, and why I think it's a field which in which we will have a lot of fun in the future? So because it's nicely bridges what I always like to do, the bridge between chemistry and physics. And we know already that there are many initiatives with high throughput calculation and so on to predict new materials, and there's this very nice approach also Alex Junger is selling since a long time of an inverse design, which is quite tough, I think, for most of the properties you are looking for. But the nice thing is with topology it works rather well, because we don't have to deal in most cases with correlation and so on. So there's really a direct connection between real and reciprocal space. And this is nice because one example I can show, and this was when we started the collaboration with Andre Bønnevik. He came to me and said he wants to found new fermions, so he needs some 8-fold degeneration points at the Fermi energy. What can he do? Okay, and I told him, look, if you want to have an 8-fold degeneration in the reciprocal space, you have to have the analog gone in the real space, so you have to have atoms in a cubic lattice, for example, sitting on the Wyckoff position, and so on. So this was like a first connection, and it's clear nowadays. So if you give me an electronic structure, it's possible more or less in a kind of inverse design to think about the crystal structure. Then if you want to have a certain band connectivity, you have to have the atom sitting on a special Wyckoff position. Then if you want to have an insulator, you have to have certain electron counting rules, and orbitals play a role. And if you want to have a relativistic effect, because this is really important in topological insulators, in physics you have the Dowing term, in chemistry we call it inert pair effect, which means, so if I have heavy atoms, the 6 s electrons are contracted. And we see this in chemistry very easily because bismuth is in the group 5. You would expect normally bismuth 5+, but it's not. It's bismuth 3+ because the 6 s electrons are contracted and they are not giving away. And this is very often the so-called band inversion. Responsible for the band inversion in the topological materials, it's the sp inversion due to the 6 s electrons. So you can predict more or less all the materials having this valence, and more or less all the heavy materials have some topology. Okay, so there are some additional conditions to make them then interesting topological insulators. They should be insulating, they should have only an odd number of band inversion, etc. But I think these are already very good rules, and they are summarized in this paper which we published together with Andre Bønnevik. The other thing is, when I was in Mainz, I was always very jealous about the ultra-cold quantum gases, like Emanuel Bloch. They could have, so Rosa, for example, liked very much to talk to Emanuel, and all the physicists liked the ultra-cold quantum gases much more than the chemists, because we made always these dirty crystals, okay? And Emanuel's crystals were always clean, because they were not real crystals, but anyway, so you can have ultra-cold quantum gases serve very nicely as model systems for real crystals, okay? And now we are very proud because thanks to topology, our crystals became very popular again. So, because now we even can sell it as serving as model system for the universe. So we are becoming friends with astrophysicists and high energy physicists. So it's really fun because we see properties in crystals which were predicted for high energy physics or from astrophysicists, and they couldn't observe so far. Okay, it's an analogy, so I have to say, because he will grill me for this. Anyway, okay, I want to talk about white semimetals because this is really the most exciting development recently, and especially the new properties we see there, and I think they are more general. So in general, we are looking for materials which show band inversion. So for example, we have an overlap of the conduction band with the valence band. Very often this happens here, the band inversion with sp, so they have a different parity. And what can happen if there's not a lot of spin-orbit coupling, this we see in some of the Heusler compounds, we have here an overlapping area, a nodal line, but depending on the spin-orbit coupling, this become a forbidden crossing area, and it can open up a band gap, so we have topological insulator, or it only partially opens up because of symmetry, and we can have Dirac or Weil semi-metals. So we end up with semi-metals, not with insulators. In case of topological insulator, we are hopefully insulating in the bulk, but this is also invented by physicists, so it's not really an insulator. Most of them are more or less bad semiconductors. Anyway, they should be insulating in the bulk, and because of the band inversion and the topology change, they should have a special surface state, which is more or less protected, which has a certain spin structure and looks like a Dirac cone. So we have this linear dispersion, which gives us all these interesting properties we already know from graphene. So if it not opens fully, so we have this touching point, very similar like graphene, and depending from where these touching points are in the Bragg zone, they are Y points or Dirac points. And so we can, if we have Dirac points like in graphene, we can even generate Y points by time reversal symmetry breaking. So if we apply a magnetic field, we should split a Dirac point, use a magnetic field into Y points. Or if we strain or remove the inversion symmetry in a crystal, we also get 2 Y points. And the Y points are distinguished from the Dirac point because they have a chirality, and this makes many of the properties more interesting. So Y semi-metal is topological between the Y points, and these Y points again are bulk properties like the symmetry of a topological insulator. So they lead to a certain surface state, which is here Fermi arcs. Then these are not a full Fermi surface on the surface of the crystal, so therefore the Fermi arcs are connected on the other side, and we have very interesting properties in this material. So this is a symbol like how the Fermi arcs on the surface connect the Y points. Okay, so Paul Klee already has thought about Weil semi-metals long time before we thought about this, so therefore there's even a connection to art. Okay, so if we look for Weil semi-metals, there are some things to prove these properties, and this was predicted originally for the pion decay in high energy physics. So what do you expect for Weil quasi-particles or fermions? So one thing I already explained, so we expect that there's a Fermi arc on the surface which connects the Y points in the bulk. But due to this very special electronic structure of the of this chirality of the Y points, we expect even more properties in case if we have a magnetic field in parallel to the current, we pump electrons from one Y point to the other, and this leads to many properties which we normally see only in magnetic material. So one is the anomalous Hall effect. I don't talk about this today. There are already a few observations where people find in non-magnetic materials an anomalous Hall effect, what we normally only see in magnetic material. The other is related to the so-called chiral anomaly. So the magnetoresistance should be negative in case if the current and the magnetic field are in parallel, and the conductivity should go with the B square. So when Andre's group again predicted together with the IOP this class of materials, so we fastly could grow them. They are also not so difficult to grow. So you take the powder, you make first the powder, and then you transport them, and you get very nice singing crystals. So the next step is then to find the Y points in the electronic structure. This is always a little bit more tricky than Dirac points because the Y points are always on non-high symmetry points. So you don't find them directly. Very often if I came to my theoreticians and said, look, I think this is a Weil semi-metal, they say, no, I don't think so, but they have no idea, and later they find some Y points, they find hidden Y points and so on. Because they are in the biggest part of the Bragg zone is totally ignored normally if we simply look for high symmetry points. And in Weil semi-metals, we exactly want to have the points at not at high symmetry points, otherwise they are Dirac points. But what is also in real life the point, I would say nearly all Weil semi-metals, we maybe found one now, have at the same time, when you have this linear crossing points in the electronic structure, you can nearly not avoid that at the same time you get electron and hole pockets. So I think graphene is a very nice case, one of the few cases which has this large dispersion, while we have really only touching points, linear dispersion, and not this electron and hole pockets. So the first thing what we did is then we looked for the Fermi arc, so we we did calculation of potential fermiarcs in the family niobium phosphide, tantalum phosphide, tantalum arsenic. We had all the crystals, and here you see you make the material heavier, 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 and it's very simple here. Spin-orbit coupling increases in the same way, and you can see nicely how nicely it compares the calculation, DFT calculation, with the measured photoemission data done by Julian Chen's group. So, and you also see nicely how the fermiarc grows with spin-orbit coupling. You see the same in the other band. It's the Rashba splitting is also becoming larger, which shows that the spin-orbit coupling increases. So this shows that this whole family is interesting. But the point is, this is why we like APES and why Engel resolved photoemission, and why mostly the first data came out from Engel resolved photoemission, because it's in some sense a very simple method, and it's less sensitive than the transport properties. So the transport properties are much more tricky. So we did transport measurements on niobium phosphide, which was our most favorite material, different than other people, and very typical for all these materials, and this reminds very much then also of graphene and bismuth, is that we have a very low conductivity and very good R values in all this material, which means the conductivity at room temperature is much lower than at low temperatures. And then if you apply a very small field, it already changes drastically the resistance, and then at higher field, it looks more like a semiconductor, which goes flat into the 0 Kelvin at 0 Kelvin temperature, which is a unique feature of all these semi-metals. It's amazing, you know, and I think there's much more behind this. People so far didn't think about this. Okay, so even in bismuth, there are some speculation, metal insulator transition in bismuth, but it's a question really what is going on. So you have a huge magnetoresistance effect, and all these materials have an ultra-high carrier mobility. Here you see already you have a significant magnetoresistance effect already at room temperature. So you can calculate the mobility, and you see what you expect for a semi-metal, that you have a change from electron to hole conductivity. In this compound, we didn't find a negative magnetoresistance effect, and we can explain it if we really look carefully on the quantum oscillation in this material. So we can, this was done with Elena Hassinger's group, you can really nicely assign all the oscillation. So this is a calculated band structure, the electron and hole pockets, and then you see these features, these lines here are the assigned frequencies seen in the quantum oscillation. So we can say we have the 1 Y point 60 millieV below the Fermi energy, so we don't see this Y point, or it's not really active in the sense of transport measurement, and the closer one is unfortunately 2 millieV above the Fermi energy. So then we asked Johannes Groth, he was at this time in the group of Cornelius Niels, whether they want to look on the thermal conductivity. So he liked to make this micron ribbon. They are very famous for their work on thermoelectrica and bismuth selenide, etc. So, and by fipping this micron ribbon, he accidentally doped the sample with gallium, what you normally don't like. Okay, our referees didn't like it too, but luckily now we were even 5 millieV below the Fermi energy with this thing, and you see, which we could easily again assign, because this even the micron ribbon shows very nice quantum oscillation. But now we see if we have the magnetic field perpendicular to the current direction, we see a positive magnetoresistance effect, not as large as in the bulk material, but you will see the size plays an important role in these materials, and we see a negative magnetoresistance in case if we have the magnetic field parallel. So this is what you expect for the chiral anomaly. So with this he was even more motivated, because there was a paper from published from Subier Sachev's group, and some astrophysicists became very active in the field of wild semimetals, because there was a prediction that if you measure the magnetothermoelectric conductance in this material, so you should see certain features which are related to something what people didn't so far see in astrophysics, a mixed axial gravitational anomaly. And the condition was that if you measure this magnetothermoelectric conductance, it should go with a B square, again, very similar like the conductivity and at high field. But here it should change from the quadratic behavior because it should diminish at high fields, and it should be aligned. There should be a strong alignment between the temperature gradient and the B field. So this was a prediction. So he did the measurement, and here's again the conductivity measurement. You see nicely the B square behavior. Now he applied the thermal gradient and measured the thermal conductivity, thermoelectric conductivity, and you see this exactly what happens was predicted is that it changed sign and then it goes nearly to 0. Okay, here the value is still high, but I think we can find now better crystals, better systems. So we saw this all together in the context of hydrodynamic theory because this was the original idea from Zubir-Sachev. One of our referees didn't like it, and there's even a report about the article, and there's now a big debate on the internet. Please join. Zubir against his enemies and so on. And Karl Landsteiner, he was one of the referees from astrophysics. He loved it paper because he ran around about the gravitational anomaly and Wiles in some time, and it fits totally to his theory. Finally, he made himself a co-author, so he's also giving comments. So if somebody wants to discuss the details about gravitational anomaly, I'm not a super expert, but it's like an interesting thing, and it makes all the people happy who are working on strange metal, like my friend Jan Zahn and so on. Now I become a friend of many people who are working in this area. So for me, it was more interesting that our observation can be understood in the context of hydrodynamic electron flow. Okay, there was also ways to interpret it more classically, because this is a recent field, and I thought it's really, really interesting because I think this is a way to explain the giant magnetoresistance effect in all this material. So this were 3 papers in Science talking about the hydrodynamic electron flow. This is one from Andy Mackenzie, and this was in some sense luck for us because he's in Dresden, and 2 papers in Graphene where they say they see evidence for a hydrodynamic flow of electrons by violation of the Wiedemann-Franz law, which means the thermal conductivity is not connected any longer to the electrical conductivity, but this you find also in other systems, which might be also interesting in the context of hydrodynamic. And here Andy saw a dependency, which is interesting, of the width of the crystal in a mesoscope on a mesoscopic scale. And this hydrodynamic electron, why I like it especially, goes back again to very old work from Steve Kiffelson, theoretical prediction. And the first measurement were done by Lorenz Molenkamp. He measured them in, I think, gallium arsenide heterostructures. And here you see the connection, which I think is there. So they found hydrodynamic electron flow in high mobility wires. So what is the idea between the hydrodynamic flow? So if you have electron gas, we always assume Drude-like behavior, which is not reality, we know also, so that the electrons get scattered at the nucleus, but if the electrons behave more correlated like water molecules in the water, so they don't see the nucleus, and the electron-electron scattering dominates the process, and you don't see the electron-phonon scattering. So this then are the predictions, so that you have momentum conserving electron-electron scattering, you see a violation of the Wiedemann-Franz law, and you see this viscosity-induced shear force is making the electric resistivity a function of this channel-wide width. So in this context, we were looking for other materials despite of niobium phosphide, and one material which we liked especially was predicted from some people from the PSI. It's tungsten phosphide 2. It's a Weyl semimetal, and it's a protected Weyl semimetal. Why is it protected Weyl semimetal? Here you see again such a band structure. You never see the band, the Weyl points, obviously. So if you see a band structure, and if you have a non-centrosymmetric structure, you should be always suspicious there might be Weyl points around there. So here in tungsten phosphide 2, we have a very special situation. It's not like in a normal Weyl semimetal, which you can think about coming from a Dirac point, which is splitted into the chiral two-folded Weyl points. Here we have the higher situation because of the crystal structure symmetry. We have a higher degeneration, so we can think about our Weyl semimetal coming from an 8-folded Dirac point, which leads to this configuration. So we have two Y points which have the same chirality close to each other, and the different chiralities much farther from each other. So we expect much larger surface state Fermi arcs, but also a higher protection of this Y points, because they cannot annihilate each other here so easily. They have the same sign. So we made again the single crystals. This is a single crystal. They look a little bit like needle-like. And this is a crystal structure. In some sense, it's not the same space group like tungsten telluride 2. So, and if you do the transport measurement, it looks again very typical for all this Weyl semi-metal, Dirac semi-metal, and so on. We have a giant magnetoresistance effect at low temperature. So at a certain temperature, we have no magnetoresistance effect in the. So this is very typical for all this material. They have no magnetoresistance, no and then they suddenly split. So if you apply magnetic field, you get a behavior like a semiconductor, and then this plateau. So this material has a giant RRR value, therefore we were very happy. But what made us especially suspicious that we had a conductivity even smaller than the conductivity which Andy Mackenzie found for palladium cobalt O2, which made him also very unhappy. So he wanted to see our data. He reproduced our data. He remeasured our data. Okay, so it's a more common feature. So then we thought, okay, this might be a system for hydrodynamic. And the nice thing here is, because this is this very more needle-type crystal structure, we could easily make wires out of this material without using a FIP. So we avoided to get this accidentally gallium doping in this material. And here are still the data from the bike. So what we do, again, in all the semi-metals, you see nice quantum oscillation. You can then assign the oscillation to the Fermi surface. And similar like in palladium cobalt O2, we have here an open Fermi surface, highly anisotropic open Fermi surface, and we have some more closed pockets. So we got already APIS data from the PSI, which shows really nicely that the Fermi surface which we calculate is a nice agreement, again, with the band structure, which means, okay, here the single particle picture works. And you see the magnetoresistance effect. This is a magnetoresistance effect in the plane. It's very anisotropic along the B axis in our material, consistent in some sense with a very anisotropic electronic structure. So simply to put it in a bigger context, these are Weyl semi-metals, Dirac semi-metal. These are the highest conductivities found in any material, so kappa. And so you see tungsten phosphide, a single crystal grown from materials bought by Aldrich and not taken care of any specific, there was no treatment. It's already really amazing, and this is unique in tungsten phosphide too. So if you calculate the mean free path of the electrons from the mobility, you get a huge mean free path, even much larger than Andy saw for palladium cobalt O2. It's 0.5 millimeter. So you can imagine this is our single crystal, and this is 300 micrometers. So the mean free path of the electrons are huge compared to the single crystal in this material. So then we thought, what should we find if we measure now the width dependency? So this is this very nice paper from Joel Moore with Andy. So where they even told us, okay, don't stay, because this compound shows a rho dependency of 1 point something. So we should find a rho dependency of the width to the square, because this is really the Navier-Stokes flow limit, while this is a still ballistic regime. So simply to remind you what happens if you have a gas and what happens if you, this is simply from the internet. I simply took it for myself. This is how a normal liquid flows in a pipe, what you do in the first semester, even the chemists have to do, and since my physics teacher is here today, teaching chemist physics. Okay, so we had to do these experiments, you know, these different pipes, the sticky liquids, and then you determine the viscosity and so on. You can exactly do the same with the electrons. Okay, so we did this. We had different widths of crystals because it was easy to split them, and then we measured here the conductivity we did it in a pseudo 4-point measurement, but we did also for control measurement a 4-point measurement. And you see exactly at the temperature where you see this deviation with the magnetoresistance effect, you also see a deviation as a function of which. This we already saw in niobium phosphide. So niobium phosphide, if you make it micrometer smaller than the mean free path, and the mean free path in this material is very large, you see a dependence from the width. So then if you look how the resistivity behaves with the width of the single crystal, you see, as you expect, there's nothing happening in this area, so it's still Drude behavior, there's no width dependent. And this is a ballistic width dependent because it goes with a 1. And this is a hydrodynamic width dependent. You see in this material, you see Drude behavior, then it goes really to the hydrodynamic regime. So where the plateau is, we are fully in the hydrodynamic regime. So the electrons don't behave like a Drude gas. They are not scattered by the nucleus. So then, so simply to remind you, you know, it's really interesting. You have this magnetic field dependence, you have the width dependent, and this looks really like a hydrodynamic dependence. So I asked Johannes, so we should find out. Here something similar must go on. So we should get the same behavior. It looks like we get the same behavior in a magnetic field as we get into if we make this material width dependent. And this is simply for comparison the palladium cobalt O2. My feeling is that it depends from the material, and we were lucky with tungsten phosphide how far you go that you really reach this hydrodynamic limit. And palladium cobalt O2 is more metal, it's not a semi-metal. Then we did the second experiment, since Johannes is from the thermoelectric field, he could do this thermal conductivity on a freestanding micron ribbon, and you see the conductivity versus the thermal conductivity. And it shows a very similar behavior like the width dependent. You see also the violation of the Wiedemann-Franz law starts when we see the deviation here from the magnetoresistance effect or magnetoresistance or from the size. So it's very similar like in case of the size defect. So you can then also determine a viscosity for a material, and I think it's in the order of magnitude like water, and it's comparable what Andy found for his material. So then I thought we should make really now the connection to the magnetic field behavior, maybe to understand this magnetoresistance effect, which we find, I have to say, in all these materials, in cadmium, arsenic, in bismuth, in all these materials. And so he simply looked then up what is the magnetohydrodynamic model. So this was developed for plasma physics, for high energy physics, and it gives you also, and you see then we did the rho width square versus the magnetic field for different widths of the crystals, and they all lie together on one line, and they are easily fittable with this magnetohydrodynamic model, which originally was made for plasma. So it seems to be that the electrons are in some magnetic orbits, localized, so the profile in a magnetic field looks very similar like the profile we assume in a liquid. And then from this data you can calculate the momentum relaxation time and the thermal energy relaxation time. And this is very interesting. So, and compare it, this was an idea also from Johannes, so to compare it with the Planckian dissipation bond, and you see at high temperature the momentum relaxation time dominates. We still have electron-phonon coupling, and at low temperature the thermal energy relaxation time dominates, and they are lying on the Planckian dissipation bound. Okay, so I think I'm nearly gone, but I think we cannot, we can even continue our work thinking about topological metals. We had a nice paper on gold, which is a topological metal, but also the whole story about hydrodynamics started with MO phosphide, a triple point topological Fermi ion system, which is more or less a metal. But also here we see that the conductivity in this material is much lower than copper, and here again we found even in the metal a high mobility, electron mobility. We find still a Hall effect, which gives us a kind of high electron mobility, and we find, I don't say it, so we find a magnetoresistance effect, which is not as pronounced. It's very similar like palladium cobalt O2, and in this range, we have also violation of the Wiedemann-Franz law, etc., etc. So there might be more materials which have this giant magnetoresistance effect where we can explain it with the hydrodynamic flow. Okay, I think there's a lot to do, and I think we should look more even beyond simple electric transport in this material, and I think now we are looking forward to see this in magnetic materials, etc. And this is a prediction from some astrophysicists who want us to look for the Hawking radiation in Weizsäcker method. Thank you very much.